Go ahead.
Okay, let B E equal to this integral so we have two questions here. First one is that we want to prove that the I converges.
Okay.
So prove that I converges. And the second question is to deduce the value of its limit.
Okay.
So I will let you solve this, Professor
Okay.
Ahmad.
Thank you. I will do it in my way,
Okay.
and after you can do it in another way if you want. Okay, so here for me what I notice for this function inside, I noticed that like we have a problem at 0 because the limit it will be minus infinity, and also we will have problem at plus infinity. That's why the idea here is to split the integral into two integrals from 0 to 1 and from 1 to plus infinity for the same function. If we can prove that this one is convergent and this one also convergent, so this integral will be convergent. So I will start here from this one. So the idea here, we will start from the integral from 1 to plus infinity of ln x over 1 plus x squared dx, and we will try to prove that this integral is convergent. So the idea here, we will notice that when x is bigger than 1, we will have like ln x positive and everything here is positive. So I will try to do this, ln x over 1 plus x squared. This will be less than ln x over x squared. And this is exactly 1 over x squared times ln x up to the power of minus 1. And this reminds me about Bertrand integral. So Bertrand integral, from this we can deduce that the integral from e to plus infinity of 1 over x squared ln x up to the power of minus 1 dx, this converges. Okay? Because here we have, like in Bertrand integral, we have alpha is 2 and beta is minus 1. So since alpha is strictly bigger than 1, it doesn't matter what is beta. So this integral is convergent. So from this, and like from the comparison, we will deduce that the integral of this from e to plus infinity, so the integral from e to plus infinity of ln x over 1 plus x squared dx converges. So this is okay. And now, but like the goal here is to prove that this integral converges. So we still have like a part from 1 to e, and from 1 to e it's clear, from 1 to e ln x over 1 plus x squared dx. This also converges since this function is a continuous function on a closed integral. So now, since this integral is convergent and this integral also convergent, we will have this integral convergent. So we proved this. So this is the first part. We proved that this integral converges. Now we will move to the second integral. Okay, sorry. The second integral will be from 0 to 1 ln x over 1 plus x squared. Instead of doing like the same thing, we will try to find a relation between this integral and this integral by a change of variable, which is y equal 1 over x. This will give us, like here at 0 when x is at 0, y it will be at plus infinity, and 1x, when x is 1, y is 1. And after ln x will be ln 1 over y over 1 plus 1 over y squared, and dx will be minus 1 over y squared dy. Okay, and now we can just simplify. It will be the integral from plus infinity to 1 minus ln y. Okay, we can use it like this. Here we will have here 1 plus y squared, and here also we will have minus dy, minus 1 here. And this will give us minus the integral from 1 to plus infinity ln y over 1 plus y squared dy, like this. And this integral is the same integral that we already proved that it's convergent. So this integral is convergent, and we can call this this value, for example, e1. So we proved that if this is e1, we proved that e2 equal minus e1, and then e2 is also convergent, and then the sum, like we can move this, and we will have e1 plus e2 equal 0, and e1 plus e2 is our integral e. And we are done. In one step we proved that the integral e is convergent and its value is 0. Okay, Laji, now it's your turn to prove this result for this integral.
Okay, so first of all, thank you Ahmad for this nice demonstration. I will now use a new method to prove that I converges and to estimate its limit.
Okay.
So first of all, we will define this integral as the result of the convergence of a certain function.
Okay.
That I will call f.
Okay.
F of epsilon, this is equal to the integral starting from 1 over epsilon to epsilon of ln of x over 1 plus x squared dx.
Okay.
And what we notice here is that f converges to I when epsilon converges, like it's going toward infinity.
Yeah.
This is exactly equal to the limit when epsilon, let's see, I equal to the limit when epsilon goes to plus infinity of f, which is equal to this integral.
Yeah, that we are looking for.
Exactly. And we want to prove that f converges. So one beautiful way to do that is to get the derivative of f.
Okay.
So f prime of epsilon equals what? So here we have a function. You know? So it will be, okay, I will take here, I will take here.
Yeah.
This remember us a formula,
Okay.
you know, of like the generalization of the derivative of functions defined by integrals
Okay.
with bounds. So it states that for f of x equal to the integral starting from this one to a certain g of t dt, we have that f prime of x equals, you will get the derivative of a first. So a prime of x, we will take g at that function. So g a of x minus the derivative of b times g at the value of the function. So we will use this formula to get the derivative of f of epsilon. So let's do that. Okay. So now that I show the formula, let's use it to get the derivative. So f prime epsilon equal to, here is our a of epsilon. And if we get the derivative, it gives 1. So we directly take g of, here is x, or g of x at its value. So it will give ln epsilon over 1 plus epsilon squared minus the derivative of 1 over epsilon. So this one times this one. So we have minus here. Minus times minus is plus.
Plus.
So you have plus 1 over epsilon squared times g of x at this value. So it will give ln of 1 over epsilon. 1 plus 1 over epsilon squared. So we will do like some calculus. Ln of 1 over epsilon is minus ln of epsilon. And this one, it will go down and it gives. So here you have minus, so ln epsilon. And if it goes down, we have here it will give 1, so 1 times epsilon. What is this?
0.
0. So we prove that the derivative of f is 0. What does it mean? That f is a constant.
Yes.
So it's like for any epsilon belonging to R, and especially like R plus.
R plus.
You see that? Star.
Yeah.
F of epsilon equal a certain constant. And in our case, this constant, of course, is the limit.
Yeah.
So how can we get this limit?
So we, at this like step, we proved that
f
the
converges.
that the integral e converges.
Because like any constant function is convergent.
Yeah.
Exactly. So how now to get like the value? So we can notice that here, as we said, for any epsilon belonging to the space, we have that f of epsilon is constant, is the same value.
Yeah.
So I will take like any value of epsilon here will give us the limit. So in particular, if I take epsilon equal 1, it's like I'm shrinking like the interval of integration.
Yeah.
So that's it. So this is exactly equal to f of 1.
Yes.
What is f of 1 here? Is the integral starting from 1 over 1 is 1
Yeah.
to 1
Yeah.
of ln of x over 1 plus e squared. Any integral starting from a to a is 0.
Yeah.
Because it's like you are like integrating over an unknown space.
Yeah.
So this is
Yeah.
so this is another beautiful way to prove that f is convergent, and we get the limit without doing any change of variables or anything like this, and without applying any theorem.
Yeah, it's a very nice proof, very nice way to do it. Thank you, Ladji, for participating in this video.